We have this unique capability of bringing together HPC, AI, and quantum computing all together. We also have the most reliable logical qubits coming from the quantum computing side on record. And so you have very advanced capabilities coming across all of these technologies, right? Advanced capabilities coming together, integrated together, and then on top, you can drive and discover with Copilot.
Microsoft has provided access to quantum computers in the cloud for about 4 years. A lot has changed in that time, including the generative AI revolution. It's now possible to create quantum circuits with the help of Copilot. Users can also work on advanced scientific problems in Azure Quantum Elements. We cover all that, along with the latest logical and topological qubits, in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the Distinguished Engineer and VP of Quantum Software at Microsoft, Dr. Krysta Svore. Welcome to the show.
Thank you so much for having me.
Yeah, can you start by giving a general introduction to Azure Quantum? I believe you had a thing or 200 to do with how it took shape.
Yeah, absolutely. So, of course, maybe if we just start, why do we care about something like Azure Quantum? Why do we care about quantum computers, right? It's really that we want to accelerate scientific discovery. These machines, right, at scale, along with HPC and AI, promise to help us solve problems that we can't otherwise solve with our classical digital technology alone, or even with, AI on top, right, or with. So it's really important that we have an integrated set of capabilities, really an integrated platform that covers HPC, right, so your cloud compute, along with integrated alongside AI and, right, quantum computing, right? So you want quantum machines in the mix to help you solve some of the most challenging pieces of some of these workflows, right? Some of these workloads where you're looking at chemistry, material science, right? Really at the core, we're trying to understand quantum mechanics, right? What are the electrons doing? How are they dancing, right? How are they interacting? Mm-hmm. And we want to do that very, very accurately. And so that's where the quantum computer comes in. And so with Azure Quantum, it's all about setting up, right? Making it easier for scientists, researchers, people all around the world to perform scientific discovery, right? So we really want a platform that enables people globally to take AI alongside HPC and quantum, right, and solve new things with it that we can't do otherwise.
Yeah, it's a great answer, because when I think about cloud access to quantum computers, I always think of it as building what people are already used to, but just adding in quantum. It'll be one more thing you pull down. Do I need 6 GPUs? Mm-hmm. Well, I also need a QPU, like that kind of thing. And that's why I always love that approach. So by now, most people, speaking of AI, most people have heard of Copilot and how it's changing how we interact with our computers personally. So how does it work with Azure Quantum?
Yeah, so when we think about these these new types of workloads that we want to be able to do, where we're taking the HPC, AI, and quantum together, right? Ultimately, you want a capability that helps you put that workload together, right? Let's say you're a chemist and you have no idea how to program a quantum computer, or you're an expert in quantum computing or quantum information science, and you have no idea the problems that chemists might be facing, just as two examples, right? So the idea is that we want to make it really easy, no matter where you sit in this kind of diversity of fields, no matter where you sit, we want to make it possible for you to bring that QPU into the fold, right? To accelerate the right problems with quantum computing. And so, part of that is learning, where should you use a quantum computer? How should you how should you program it? What functions or subroutines you might say? What actions should you ask the quantum computer to go do, right? So Copilot, this Copilot in Azure Quantum helps ground you in the capabilities of quantum computers, right? How do you program them? It can help you write your first programs in Q#, for example. At the same time, if you're more of a quantum computing expert and you want to learn more about, what kinds, you have this great maybe new quantum algorithm or quantum idea, right? And you want to see how could this help in the space of chemistry and materials science, right? This is now a more natural language-based interface to ask the right questions, right? To ask questions about how that fits together, right? I want to understand more about, the chemical nature of something, the ground states, right? The energy spectrum, et cetera. So it's really about opening up that communication, those capabilities across disciplines, but doing that from a natural language format, right? So Copilot in Azure Quantum today really enables you to write programs across these different workloads to better understand quantum computing on the one hand, say chemistry and materials science on the other. And it's especially trained further for this set of information.
Yeah, that's great. And I'm glad you keep bringing up the science aspect, because let's all remember where these machines came from. They were originally dreamed up by Feynman to simulate the quantum universe we live in. And I see so few people actually using them to do anything even remotely in the scientific realm like that. Everyone's, of course, interested in real world use cases for like optimization things, but I do want to, lift the veil and peek a little deeper into the universe. So that's pretty exciting. And on that note, how does Azure Quantum Elements expand what use cases are possible?
Yeah, well, I think, maybe let's first dig into the point you just made, right? These machines, right? A quantum computer, it's quantum, right? So at its core, it's called a quantum computer because inside, right, it's taking advantage of the principles of quantum mechanics, whether depending on kind of exactly how you're building it. In all cases, though, it's taking advantage of quantum mechanics to do that compute, to store information, and then ultimately output a solution, an answer, right? A set of classical bits. So we really do need to understand, how are these machines different, right? How are they different than our digital classical machines? And what are they really going to be good at, right? Because we don't want to ask a quantum computer to solve just anything. We want to ask it to solve the types of problems that really are hard for our classical computers today, for AI models today, and so on, right? So it's important to really understand what they're good at. And when you look under the hood, just as you said, right, and as Feynman, originally laid out years ago, right, they can be really good at understanding quantum mechanics, right? It's a quantum mechanical system at its core that can really understand quantum mechanics. And so this means that we can understand things and evolve, Hamiltonian's, Schrodinger's equation. These are the equations that really govern much of nature, right? The quantum mechanical world is spelled out and actually specified by quantum mechanics, right? By a Hamiltonian, by Schrodinger's equation. We want to understand what happens over time in a material system to a molecule, right? In a chemical reaction, right? At the core, we need quantum mechanics underneath that. So then when we think about the fact that these machines are really well suited to understanding quantum mechanical problems, we can then look and see, where are the hard problems here for classical computers? And it turns out, especially when electrons are really correlated in a system, this is hard for classical computers for the most part. And so we want to then run that part of that solution on a quantum machine. Turns out this is really in the space of chemistry, for example, materials science. So when we think about catalytic chemical reactions, really understanding what happens in that reaction to very high accuracy for a number of cases, right? We need the quantum machine. And then similarly, in the space of materials, we want to better understand maybe exotic properties of materials. We want to know if a material could superconduct at higher temperature, right? We need to understand these materials models and what's happening at the electron level in these systems. And so this is what we want to use a quantum computer for. And I raise that in the context of your question around Azure Quantum Elements, because what is elements? I mean, even the name, right? Elements, It speaks to something about the periodic table and the atoms involved and potentially the electrons involved, right? And so it's really about enabling right? Bringing HPC, AI, and quantum computing together and enabling scientists globally to make more accelerated discoveries in the space of chemistry, material science, and ultimately science more broadly. So Azure Quantum Elements is about bringing these different technological capabilities, right? Cloud compute, AI, advanced AI models, the ability to simulate different physics aspects of physics more quickly by using cloud compute, and then also then bringing a quantum computing capability into the mix, right? Integrating that alongside for the pieces of the problem that are really hard for the classical compute and AI models. So I think of it as this layering. Azure Quantum Elements it's a lot like a kind of a layer of different solutions, different capabilities that you string together, right? That you really bring together to solve a problem, and and ultimately it's a platform, right, to accelerate this discovery. And a great example is what we did with Pacific Northwest National Laboratories here, where we really sought to find a better makeup of a battery, right? So you want to replace ultimately the lithium with something that is a less scarce resource, right? That has better properties in terms of, say, combustibility or otherwise. And so with PNNL, we used this Azure Quantum Elements capability, right? Where we were able to generate 32 million candidates for this potential new battery material, 32 million candidates. And then through a series of computations, and in this case, we did not use the quantum computer for this problem, but we used a series of AI models of accelerated simulations that were ported to the cloud environment to make them very fast to understand the physics in a given material. And through a series of these, in 80 hours, we were able to take that 32 million candidate set and drive it down to 20 candidates. We then chose one with Pacific Northwest National Laboratories to synthesize in the lab, and it works as a battery, and it has 70% less lithium than batteries today. So this is a great discovery through the Azure Quantum Elements pipeline.
That's really well described. That's amazing. Yeah, that's obviously what Feynman was thinking of. This ability to simulate reality, and he just probably couldn't dream of the AI assistance that he'd get along the way. And I know we're going to have all sorts of issues with as we use green energy. How do we store this? And we do need to look for other materials. So that's going to be hugely important going forward. Are there other ways that Azure Quantum differs from other cloud platforms? Because so far you've already given examples that show that workload, right? That show, a little bit of AI here, HPC here, quantum here. And if you have any other examples of how it's different from other cloud platforms.
Yeah, so here, we really want to make sure that it is a platform, right? Bringing the different tools, the different models, the different pieces together, right? So we want the best-in-class capabilities across the platform for our scientists and researchers and, for people worldwide. So it's really about bringing these things together and making it easy, right? Much, much easier, bringing that acceleration forward. So we want to see, right? We want to see this, I mentioned 80 hours, right? In the course of 80 hours, going from 32 million candidates down to 20 in the case of the battery example with PNNL. That is what we want to bring forward in this platform, right? So the platform needs to be efficient. It needs to bring the right models forward. It needs to be able to operate over a variety, right? Many, many different types of problems that you might want to solve here. And so we have a number of pieces there that come together. We have a generative AI capability. We have an accelerated DFT model, which is a model often used in physics to understand the underlying structure, right? And then, of course, we also have quantum computers that you can plug into the mix. And on the quantum computing side, not yet can these quantum machines, right? No matter what quantum machine you're looking at in the world, these machines can't yet give you something you can't do classically. But we are, very much progressing through the capabilities, right? The levels of capability of quantum machines, getting to the point where you will see scientific advantage. That means seeing advantage from getting a solution from the quantum machine for scientific problems, right? We are fast approaching the point where we will see that advantage coming from the quantum machine being in the mix. So that will give you the ability to do something you can't otherwise do classically. And so really this platform, Azure Quantum plus Azure Quantum Elements, right? I think what really is unique to other platforms, right? Bringing together HPC, AI, and quantum computing all together. We also have the most reliable logical qubits, right, coming from the quantum computing side on record. And so you have very advanced capabilities coming across all of these technologies, right? Advanced capabilities coming together, integrated together, and then on top, you can drive and discover with Copilot.
Great. Yeah. And we're going to talk about a couple of these newer announcements and newer achievements. We're going to get to logical in a little bit. Can we talk first about the recent work with Photonic?
Absolutely. So, one of the things when we think about, our approach and what we're doing in the quantum ecosystem, right? You need different pieces. So before just jumping into what we did there, I think it's good to understand there are different pieces across different technologies needed across the quantum ecosystem, right? So you have quantum computation, which we've been focused on in our initial discussion here, right? Where you're wanting to compute something, right? So you need to be able to operate that much like we do a classical computer in many ways, right? You need to be able to program it. You need to be able to ask for a solution, right? So that's quantum computing. We're going to ask it to store and process information just like we do classically. But in that, when we look at our classical compute ecosystem, we also have networking, right? You and I are discussing right now via the internet, right? A very important network that all of us use all the time, every day. And it's a classical network, right? Classical communication mechanism. So in the quantum ecosystem, you also want to be able to explore how would you share quantum data, right? Quantum information, not just classical information, but quantum information. And interestingly, like there are sensors in the world that collect quantum information directly, not just classical bits, but quantum information, quantum bits of information. And so we need to be able to transport this information. We need to be able to share this information, distribute this information. And so we call this quantum networking, right? So the ability to communicate over a quantum network, a quantum channel, share quantum information instead of just classical information. And this won't replace the classical internet, right? This is not something that gets rid of the classical internet, just like quantum computers will not replace your classical computers. It will be an additional capability alongside classical compute and integrated with classical compute. And something, similar is true of the quantum internet, right? And quantum networking. We still need our classical internet. We still need classical communication and classical networking, but this would integrate alongside and offer new and different capabilities that we're still discovering, right? Exactly what we could do if we're able to share in what's called entanglement. If we can share quantum information and quantum entanglement across a network, it could open up a huge number of possibilities, including what you might think of as a quantum internet. So with Photonic, we are looking at how to share this entanglement. How would you distribute what we call entanglement, this quantum information? How would you set up an early version of that network and then grow that network to the point where it's as big as a quantum internet, right? And so first you want to show that from point to point, you can establish that quantum connection and share quantum information from point to point, from point A to point B. Then you want to be able to enable a more complex network, for example, where you share from maybe, say, a hub to many different endpoints. And then from there, you want to build out and connect many of these almost like stars, right, together into a more complex network, much like our classical internet. And that would be a quantum internet. So with Photonic, we're working on these steps, right, going from this point-to-point capability to a more complex hub-spoke capability to ultimately a quantum internet. And what's neat is this technology can also be be used to connect quantum computers. So we think about cloud computing, data centers, distributed classical computing. This is all enabled by networks, right? Data centers are full of a lot of networking technology. And so with a quantum computer, if we want to connect it to another quantum computer, we're also going to need a quantum network there. And so what we've done with Photonic most recently, what we've shared is that together, in collaboration together, we've been able to establish a point-to-point capability, right? So Photonic has, for example, they have a system at each point. This is separated by roughly 40 meters of telecom fiber. So everyday operating environment, right? The type of fiber that we already use in data centers today. You have 40 meters between 2 points, and they were able to establish basically quantum communication between those 2 points, share entanglement between those 2 points, and then ultimately actually process and perform an operation between those 2 points over that network. So it's a great step forward, and we're really excited about that capability that Photonic recently demonstrated.
So you visualize that as of course, enabling something like connecting quantum computers together operate as one, right?
Yeah, for example, it can be used to realize what we would call distributed quantum computing, which in that scenario would be exactly as you're saying, right? You could have a quantum computer that all is housed in a single unit. That's much like the approach we have also at Microsoft called topological quantum computing, where all of your qubits would sit on a single chip. But another way to realize quantum computing at scale, right? This is when you need many, many physical qubits, upwards, say, of 1 million. And other ways to realize that is to have many, say, chips or points, units, and connect them with a network. And so this is another way to realize distributed quantum computing with this quantum network.
Yeah, you teased the topological word, and we'll get to that in a bit. Everyone just has to wait for the juicy stuff there. So what business use case impact do you foresee with this distributed entanglement, and the long distance communication realm? There's a potential, like you said, to interact with those physical layers. And are there any use cases that maybe an end user won't even really know they're working with a quantum computer or something because it's involved in the mix when it comes to communication or anything like that?
Yeah, I think at some point in time, over time, right, especially with the ability to have something like Copilot set up workflows for you over time, right? You can really look into the future and imagine that at some point, right, you're only communicating with maybe your natural language, right? And so maybe behind the scenes, you don't actually need to know what processor is running what part of your workload, right? And this would be true even of just classical processors, but no doubt also maybe with a quantum processor in the mix. So it may be the case, in the future, and I definitely think that's true, that over time, right, you'll just ask, you'll ask the platform to put together the solution it needs to go do, and it'll do it for you, right? Now, in terms of the business cases here, I think it's really building on what we've already talked about, right? Ultimately, we want to be able to solve solutions that we can't solve classically that really offer advantage over what we can do with classical capabilities. And you could divide those out maybe into networking and computing, but at some level, it's really what can we do within this quantum ecosystem that we can't do classically. And so indeed, right, this network, as we just discussed, right, could enable distributed quantum computing. In other words, another path to build up a larger quantum computing capability, which would allow you to, ultimately we need quantum computing at scale. That means we need a lot of qubits, right, a very large quantum computer, ultimately to perform, for example, high accuracy calculations for things like catalysis. And so if we want to understand how, say, nitrogen fixation works, right, which is the process we use behind artificial fertilizer production. If we want to understand that in detail enough to replicate what is happening with microbes in the soil so that we can produce that industrially, locally in different regions of the world, we need really high accuracy solutions. And this needs a lot of qubits, upwards of 1 million physical qubits. And so this network could enable a path to scale up to 1 million physical qubits. by enabling a multi-module architecture to get there. And at the same time, as I mentioned, right, it can unlock something like a quantum internet, right? A way to share quantum information in new and different ways. There are quantum sensors in the world that are extracting quantum information, right? This is a way to now take that information,
Keeps
learn from it, right? Yeah. So it's, I think we don't know. I think we're just scratching the surface on what distributing entanglement, sharing this quantum information really means, right? It's a totally new resource that we know it can help with quantum computing and building a quantum internet. But there's a lot of opportunity there to figure out how sharing this entanglement can help other, drive forward new and different ideas that we really haven't thought of because we haven't had it right at our fingertips. But ultimately, right, you can use it for different, potentially for different security capabilities, different information sharing capabilities. You can potentially use it so that you have better kind of signatures or understanding of what's really happened to that information as it's been shared. But ultimately, also, you can use it for quantum computing.
And on that note, when I think of the march toward fault-tolerant quantum computing, I still hold a place in my nerdy heart for topological. I think I've been talking about topological in public as long as your team has been working on it. Basically, whenever I always bring it up, because it's just it has such promise. Can you discuss the status of that effort along with Microsoft's roadmap for achieving quantum
at scale? For sure, and. Yeah, it is. I'm glad to hear that that you have a love for this area. It's an absolutely fascinating, right, and beautiful theory. On top of now we have beautiful devices, right? So we've also engineered beautiful devices to match this beautiful theory. So why do I say it's so beautiful? I think here it's this approach to quantum at scale, right? Why are we doing it? Why do we care about topological quantum computing? We want to get to 1 million physical qubits and beyond, because that is critical for being able to unlock, just solutions across, as I mentioned, catalysis, materials design, right? Materials prediction. We want to understand what's happening at that subatomic level in detail so that we can help quite literally feed our planet and save our planet, right? We're talking about solving problems that we all should care about deeply, right? Because we really need to understand how can we help extract carbon dioxide from our atmosphere? How can we do that efficiently? How can we do that well? We need to understand the reactions at hand there, and we need them in detail to mimic industrially. Getting it in detail to high accuracy needs a quantum computer, but that quantum computer needs to be large enough to hold those calculations and output the solution we need to high accuracy. So large here, we need upwards, of 1 million physical qubits. So when we look at architectures for enabling that, we just talked about quantum networking being one path to enable a kind of a more modular design. But another path is to consider a single module and to put everything on a single chip for that 1 million qubit scale. And the topological qubit enables or promises that type of path, right? We can fit millions on the size of the chip on your credit card. So they are small enough to fit there, but they're not so small that you can't wire them up and control them, which is super important. We have to be able to program this device, right? We have to be able to get literally a computer program onto it, operate it, right, and extract a solution. So it can't be so small that you can't fit wiring there. And there are some qubit designs that are quite small, right? They're very hard to wire and thus very hard to control. So these topological qubits sit in the sweet spot of being the right size. They're controllable digitally, making it an easier control stack. And they're fast, right? They're fast enough to do a computation such that we can get a solution in a month or less, right? We don't want to be waiting millions of years for the quantum computer to produce a solution. We really need these solutions in a matter of weeks or days, but not years or, even longer.
This sounds like
So
the opening to a disaster movie. Like, we
yeah,
need the solution now. No.
that's right. We need it now to save our planet and save humanity. So, really, it has the right speed, controllability, and size. And in addition, it has this intrinsic ability to handle noise, right? So by design, topological qubits can combat much of the noise that qubits face. And it can do that in the physical device. This is different than other systems. Other qubit designs require extra qubits, many extra qubits, to help protect them against the noise of the environment, right? Qubits like to interact with their environment, and that means that they become too noisy, right, to trust the solution. So we need reliable qubits. We need to be able to have them be protected from the environment enough, and not so noisy that they collapse or give us a wrong answer. So the topological qubit, not only has this right speed, size, controllability, but additionally, it has this intrinsic property that it can really handle quite a bit of noise just by its physical design. And this is a great thing because it means you have fewer physical qubits required for a given solution, right? Ultimately, you can create what we call better logical qubits here with fewer resources required to do so. And so this, our topological quantum computing work is really focused on enabling a quantum machine at scale, doing that efficiently, and enabling that to be in a small form factor. You don't want the thing to be the size of a football field, right? That's very hard to control. So really it is, as I said, like the size of the chip on your credit card. And so right now, we have made a series of progress here, right, where we have devices that show the properties required. I mean, this is pretty amazing, and part of the beauty here, right, is that it's a new phase of matter, right? So these qubits require really understanding exotic physics and showing some of this exotic physics for the first time. And so we did that in the last year, where we were able to show that we can quite literally engineer, right, drive this device into this new phase of matter called a topological phase of matter. And then from there, we need to be able to control that, so that we can store information in the device, operate the device. And that's what we've been able to do more recently, is to be able to read out the device. We call it a Majorana parity readout, but we've been able to read out these devices. And so now it's really about bringing these various components together to be able to operate it fully as a qubit. And that's what we're working on.
And then we'll need multiple of them, of course.
Absolutely, yes. Then you indeed, start to stamp it out, tile it out, if you will, to build up to a larger and larger quantum machine there.
Quantum breadboarding.
Yeah.
You're like plugging it all together. It is a bizarre state of matter. The guy that came up with it originally literally vanished after he thought of it. So who knows? Who knows what happened? If you feel free to Google Majorana, but interesting life story there. So do you have any sense of like timeline for this march to scale? Like how long before you expect to see? I realize you can't say 10 qubits this week, I know, but just like a general idea of like, of what we can expect.
It's, I mean, as you probably know, right, putting innovation on a timeline is tricky. At the same time, we are looking at years instead of decades to get to the point where we have a scaled machine here.
And the beauty is, if I'm understanding correctly, that the number of qubits you get are pretty much going to be the number of qubits you get, as opposed to like 1,000-to-1 ratios or something for transmon that would be required.
Yeah. So indeed, the overhead to reach that scaled quantum machine is less for topological, and that's for topological qubits, and that is why it's a very important and promising approach, right? We we love the topological qubit because it promises less overhead needed to correct these errors, as I mentioned, right? Intrinsically in the physical design. And this is the whole idea of topology, right? That you could stretch and perturb the system and it won't incur an error. And so, here using it as a quantum machine, we really do have an advantage because the physical device itself promises to protect some of the information we want to compute and store in it. And that's just really important. And so it results, as you said, in less overhead for that ultimate scaled architecture and scaled machine.
That's great. And I guess we could switch gears just quickly to a qubit that is running right now. So there have been a few logical qubit announcements this year, including the Quantinuum achievement with Microsoft. That was pretty amazing. It was, I guess, 7.5 to 1 physical to logical ratio. Can you talk just briefly about that and how it might have changed your assessment of a timeline for error-corrected systems appearing in general?
Absolutely. I think it's really, we can look at the capabilities of a quantum computer in rather simple terms, if you will, right? At first you have qubits available in a quantum computer and you operate them in that form, right? What I mean is you directly store information in the physical qubits themselves. You compute on them. We call this noisy intermediate scale quantum computing, NISQ, for those of you that have heard it. And this is really level 1, right? Where it's foundational, right? You're operating on those qubits in their physical form, not doing any extra on top, right, to get better results, or maybe a little classical processing or something like this. But ultimately, you're operating on the physical qubits themselves. And that's level 1. And the thing is in doing that, right, these qubits are noisy, right? Physical qubits are noisy. And so you're limited in how much compute you can do with them and still get it, while still getting a reliable answer. And so ultimately, we need reliable solutions from our quantum computers, right? So we can't get that, right? We can't get deeper, more complex computation and a reliable solution from NISQ machines, right? From level 1 quantum computers. We have to advance. So at level 2, the next level is to use these physical qubits more as a unit. I like to think of it as what I call qubit virtualization, right? It's like taking a pool of physical qubits, some number of physical qubits, and treating them like a virtual qubit, right? So, and that's, that virtual qubit is then what you use in your algorithm that you use to get your solution, right? So you take a pool of physical qubits, you treat them as a unit, operate them as a unit, and then this becomes the type of qubit. This virtual qubit is used at the algorithm or program level. You might also hear of these as logical qubits. And so level 2 is about logical qubits, right? It's about reliable quantum computing, where now by using this virtual or logical qubit, I can get more reliable solutions out. And maybe, in this level, I imagine driving to say 100 logical qubits or more, and you can see, for example, at 100 logical qubits, when those qubits are good enough, you can see advantage for scientific problems by using this quantum machine. And then you graduate to level 3, right? Level 3 is all about scale. And there you're looking at thousands of logical qubits. That's what you need for problems, for example, in catalysis, right? For more of your commercial, industrial style problem, level 3, you're going to need upwards of thousands of logical qubits that are very, very good and enable very deep computation. And that's scale, right? That's level 3. And so today, all quantum computers are at level 1. Except now, right, with Quantinuum, as you mentioned, right, in April, we shared that we were able to show the most reliable logical qubits on record. We showed 4 logical qubits that are 800 times better than their physical counterparts. And now, I can say we have graduated from level 1 to level 2. And so we are in the era of, reliable quantum computing now. Now, with that said, we still want to advance as rapidly as we can towards scale, right? Because at scale, we unlock these commercial, industrial problems that can help us, as we talked about, feed and save our planet. But with that said, at level 2, right, 100 logical qubits, even less than that, at 50 to 70 logical qubits, we can show things we can't show classically. And we can, at 100 logical qubits, have solutions coming from that quantum machine for scientific problems that we can't get classically as well. So this is a very exciting period in the next couple years where we look at what are we, advancing to 100 logical qubits and beyond, and showing things with those logical qubits that we cannot achieve with classical machines alone.
Yeah, it's so exciting because it allows us to make a pretty strong prediction. Even if we don't know exactly which paper is going to appear in the future that shows advantage, once we have a machine that can't be simulated by an emulator, then you have to have advantage, right? You just have to.
And it's why we're building these machines, right? We want quantum computers because we want them to be advantageous for a set of important, useful problems.
Yeah, it's like, well, if you have a 1,000,000 horsepower engine, I can guarantee it's going to break some record. We just don't know what. Maybe biggest explosion on the track. I don't know, but it will be something. So, are you exploring any use cases where, even though we have still kind of more unreliable qubits, where you believe you might see some early quantum advantage, anyways?
Yeah, absolutely. In that 50 to 100 logical qubit range, we can show, we will be able to show advantage for different materials modeling problems, for example, that are of strong scientific interest. And so you can explore these models with these quantum machines when you have enough logical qubits, and those logical qubits, of course, have to be good enough. So it's not just any logical qubit, similar to physical qubits. Not all qubits are created equal. That's the same with logical qubits. Not all logical qubits are created equal. We need to drive what we call the error rate on those logical qubits. So the logical error rate, we really need to continue to drive that down. So that enables, as that error rate goes down on the logical qubits and gets better, that enables us to do more complex calculations. So showing, right, when we think about use cases, what can we show with these logical qubits? As that error rate gets better and better, we can do a more complex computation that enables us to have access, right, to more problems that will be able to show that advantage. So, on paper, we work out, where that line sits, right? What problems and how big of a quantum machine will you need? We even have, for example, in Azure Quantum, another I think, big piece of Azure Quantum. It's not just running on the quantum machines, but also being able to predict how big of a quantum machine will I need for this problem, right? We want to understand how many resources will be required to provide this solution. And so we have what's called the Azure Quantum Resource Estimator. And it's a tool we use internally as well to explore where are those use cases, when do they light up in terms of the size of quantum computer that we need to do it, how many logical qubits will we need, how good will they have to be, right? So we really want to understand in advance the workloads that we're going to run on the machine. And so we've spent well over a decade looking at those types of problems and understanding the size. And it's the size of quantum computer needed and how you should design that quantum computer. And that really points to, again, to the topological qubits, right? We have identified the workloads at scale, right? What are the scaled workloads we want to run, for example, in chemistry with, say, catalysis problems, right? We know what those problems look like. We've written them down. We've done the resource estimation in detail, right? In a lot of detail, right? Where we have the whole algorithm written out and ready. That enables us then to design the quantum computer such that it can light up and successfully run that solution. And so we've done that, right, as we've designed our topological quantum computer and that architecture. We do it with the workloads in mind. That's the same at level 2 when we have logical qubits. We are designing that logical qubit system with the types of solutions we want to run, right, or yield in mind.
Yeah, that was a great answer. They've all been great answers. I want to thank you
Thank
for
you.
your generosity of time and the care you gave to these answers.
Thank you.
Before I let you go, I'm going to be including in the show notes a link to how people can sign up and try this amazing platform out for themselves. Is there a tip you want to give before we close the show? Maybe something they should try first?
Yeah, well, I do think if you're just starting in quantum computing, in this scientific space, right, this kind of crossover with chemistry and quantum computing as well, I think the Copilot in Azure Quantum is a great starting place. You can have an interaction, right, interactive discussion with the Copilot, and really identify directions for your further discovery. So I think that's a great starting place for the more general audience.
That's great. Thank you. And with that, I'll let you get back to achieving utility at scale.
Terrific. Thank you so much for having me.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. Microsoft is interested in accelerating scientific discovery in its Azure Quantum platform. It has built a way for quantum computers to interact with HPCs and AI to solve challenging problems in material science, chemistry, biology, and more. A great example is a battery that uses 70% less lithium. These projects are done in Azure Quantum Elements, and the offering has drastically reduced experimental timeframes, for example, from 6 months to 1 week. Copilot AI makes the process even more powerful, letting researchers without quantum coding experience get a head start on the best circuit approach to take, or help along the way. Copilot is available in other areas of Azure Quantum too. To advance quantum computing in general, Microsoft has been working with partners on a few exciting experiments. To achieve better connectivity to transmit quantum information from sensors or between quantum computers, they partnered with Photonic to achieve quantum networking for a future quantum internet. This distributed entanglement started at 40 meters, but the goal is to have distributed quantum computing one day. With partner Quantinuum, Microsoft helped create 4 logical qubits from 30 physical ones. These logical qubits have 800 times the fidelity of physical ones without error correction. Let's not forget that Microsoft is working on its own topological qubits, the so-called Majorana approach you might have heard of. The timeline for a working system is unclear, but as Krysta puts it, we may have these qubits in systems in years rather than decades. They'll require very minor error correction, so they could hit the quantum world with an atomic impact. While we wait for these fault-tolerant machines to come to life, you could try Microsoft Azure Quantum today using the link in the show notes. That does it for this episode. Thanks to Krysta Svore for joining to discuss all things Microsoft Azure Quantum. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.